given is the geometry, okay, and the loading condition. Okay. Now, so the first thing of all, the first thing we are going to do is we are going to locate. So number one, we're going to locate the orientation of the transformation okay, and position of the elements. Okay. So we have identified the position of the elements. Next, we're going to identify the position of transformation. So we know that this will be X, Y, and this is Z. So we are following whatever that's given to us over here. Okay, X, Y, and Z. So the next thing that we're going to do is we're going to find out where the neutral axis is. Okay, neutral axis relative to the elements. Element H and element K. Okay, we're going to locate. So the neutral axis, as you can see, is exactly on this line over here, which I'm going to draw in green now. Okay, you can see that, right? So that is the position. Okay, so this is the position. Wrong color. So this is the position of the neutral axis. Okay, that's the position of a neutral axis. So as I said, this is a 3D problem, and I'm going to teach you how to solve it in a 2D world. Our paper is in 2D, okay? So now, watch this. So what we're going to do now, based on transformation, we're going to analyze the structure, okay? So the first thing that we do is we are going to view our structure now in this view, okay? We're going to view it like this. So this is my X, this is my Y, and this is my rotation about Z. Okay, that's the rotation. So we're going to view it this way first, okay? So now we're going to sketch this out. So the height is 10. So we have a 10. So 2, 4, 6, 8, 10. And then the length is 14. Okay, so we're going to do a 14. 2, 4, 6, 8, 10. Right. Okay. So our this end over here, our this end is fixed. So the first thing to do, we draw our neutral axis. Also, don't forget your neutral axis. The neutral axis is very important relative to the element. So this is the position of our neutral axis. Very important line. Then we have point element H. So you have to sketch where your element H is. Okay. So ideally, I like to draw this in red. So this is where our element H is. Right. So element H. And then over here, this is our element K. Okay, we identify where our elements first. And then from here, we will put in our forces. Okay, we will put in our forces. So we are going to sketch in our forces. So we have a cross over here. So there is 6, 2, 4. So we have a cross over here. So the cross is at 150 pounds. So that corresponds to this force over here is going in. And then you have another force going in at 50 pounds. And then you have one force generating this direction. This is going at 150 pounds. Okay. And then you have a force coming in. You are looking at the arrow. This is 200 pounds. Okay. So anything else that I forgot? No. Okay. So now the number 3 thing that you have to remember now, once you start this drawing, okay, I'll write this down. Okay. So number 3 is do not analyze the forces okay, do not analyze the forces that are dots or cross. So those that you have drawn dot or cross, don't analyze them. Okay. So by looking at this view, okay, we only have to analyze for this view. We only have to analyze the 150 pounds. Okay, we're only going to analyze the 150 pounds. So the 150 pounds, what will this 150 pounds do? Okay, so the 150 pounds over here that we see now, it will generate a moment, right? And it will also generate an axial load. I repeat again, the moment, the 150 pounds will generate a moment, and it's also going to generate what? An axial load. So if you look at the 150 pounds based on the moment, okay, so let's look at the moment first. So at the 150 pounds, let's look at the moment. So let's analyze based on moment first. Anyone, any questions so far? You guys good? Sometimes students get confused that why is there an axial load? Yes or no? Right? Because it has an axial load, because this axial load would be transmitted to the what? To the neutral axis. Okay. Remember we had this problem before, just to quickly recap. Remember we had this problem before? Right? We had this problem, right? And then we are going to look at stresses at point C, right? And then we have a load P over here. And then we have a reaction down here, which is P prime. And then there's a moment over here. Then there's a counter moment over here. That is why we have a what? We have an axial load. Is that clear? Okay. Just to quickly recap. So that is why the 150 will create a rotating moment. Okay. So at element H, okay, so if you look at how the structure will deform, okay, if we look at the structure, how the structure will deform. So the structure will deform in this direction now. So the structure will deform this way. Right? I'm going to draw how the neutral axis will deform. Okay, the neutral axis will deform this way. Right? Okay. So with this view, more or less, we know that element H will be under what? Will be under tensile. Element K will have zero stress because element K is on the what? It's on the neutral axis. Okay. So let's look at the moment first. Okay. So let's look at the moment. So the moment is equal to force multiplied by distance. So what is the distance we will use for element H and element K? What is this distance? Anyone? Element H, is it a different distance relative to element K? Yes or no? Anyone? Hello? What your guess? How are we?
The same 10 distance.
Yeah.
And,
the distance is always the moment is always up to the what? Up to the neutral axis. Okay, so it's this distance that we're talking about now. Okay, it's this distance we're talking about now. Okay, it's this distance. It's up to the what? Down to the neutral axis, and this is our 10-inch. This distance over here is 10-inch. A lot of students get this all worked out wrong is because they do this. Okay, this is wrong. Okay, I'm not endorsing this. They say, okay, Eugene, element H, I'm going to take my moment up to here. Okay, for element H, because element H is at the surface, and given that we don't know the diameter now, so I'm going to estimate this is 9-inch. Okay, that is my moment. So element H has a different moment. Element K have a different moment. What is the problem with that? Anyone?
the moment would be less so on the 9-inch side.
Yep.
Which doesn't make sense with the bending profile that we know is going to happen.
Exactly. Some students will ask me, then where's the compensation? The compensation is here. Okay. So if you look at that, so let's calculate first. So moment about Z, right? Moment about Z axis is equal to 150 multiplied by 10. So this is equal to 1,500 pounds, right? Inch, and it's going to rotate in a clockwise direction. Yes or no? And then the formula that we're going to apply is what? Stress in X for bending first. Okay, let's look at bending first. Stress in X is equal to mz over izz multiplied by y. This y will compensate for the what? Location. Does that make sense? Is the y, it is already what? Compensating for the what? For the different location. That's why mz is equal to force times by the perpendicular distance. Oh, I need drugs to calm myself down. Too excited, cannot write properly. Anyone have any drugs, you know? And this is recorded, whatever. So y, right, is to compensate for the position. Okay. Right, and then moment about y or z, mz, I hope you all will take this like really, really seriously, okay? Is equal to force multiplied by the distance or perpendicular distance to the neutral axis. Right? So for this case, okay, for this case that we see now, it happened that the perpendicular distance for the 150 will intersect the neutral axis at what? 90 degrees. Okay, so that is our moment about Z, X. So for this case, moment of x, we know that element h. So it's good when you analyze, you do this. Element h, right? Due to moment of z, it's going to be what? It's going to be tensile, right? And then over here, then you also know that element k, right, is going to be what? 0, right? Why 0? Because if we base on that